Number 8, in a class of 20 students, what is the probability that at least 2? Okay, so we want to think about the at least formula. Share the same birthday. So the at least formula is 1 minus the probability of none raised to the number of trials, so raised to the number of students that we're comparing this with. So 1 minus, okay, so we got to think here, if I'm trying to find 2 students who share the same birthday, then I want the opposite of that. What's the likelihood that they don't share the same birthday? And so out of 365 days in a year, there are 364 days where they don't have in common. And since there's 20 students, then I want to raise that to the 20th power. And if I type that in a calculator or Excel, I should get 0.054, which means in real life that about 5% of the time when you're sitting in a class of 20 people, you'll find 2 people in the room actually share the same birthday. Number 9, the probability of raining is 0.3, and on Mondays 0.3, and on Thursdays 0.4. Assuming these are independent, what is the probability of that? Okay, so to start off with, we're assuming they're independent, which means one event doesn't impact the other. So the likelihood of them raining on both days would be 0.3 times 0.4, which is 0.12. Does not rain on Monday, and I'm not given any classification about Thursday, so I don't care about Thursday. So if it's a 30% chance of rain on Monday, that means it's a 70% chance of rain that it doesn't rain on Monday. It rains on Monday, but not Thursday. Okay, so if it rained on Monday, that was 30%. Not raining Thursday. Well, if raining is 0.4, that means not raining is 0.6. So 0.18. Okay, and it turns out let's get rid of the independence assumption. Let's say we happen to know that the likelihood of it raining on both days is 0.1. Are these events independent? Now this is not a theory. This is not a sort of your opinion question. I know sometimes at stats it sounds like they're asking your opinion. That's not what you get in this case. It literally is meaning knowing that Monday is 0.3 and Thursday is 0.4. And I also know, in addition, that on both days there's a 10% chance. Are those facts independent of each other? And so what I'm really looking at is, does 0.1 equal the probability of both at the same time? Is that a true statement? And it's actually not. Those two numbers do not match, which means the two events are not independent. Now, it doesn't mean we're going to go back and change our other answers. The first 3 parts are fine because we were told to assume independence. This 4th part is knowing this other fact. Can we still get away with saying independent? All right. Rosemary works for the U.S. Census Bureau for a particular Midwest town. The number of children per family and their respective probabilities are as follows. Those numbers there. Let's see, so I actually want to put that in Excel, and then we'll kind of use that to help answer some other questions. Okay, so what I'm going to put in is I'm just going to type in the number of children as sort of my x's. And I am going to leave a blank where I don't know the number, because Excel can kind of help me with that. So 0.07, 0.1, or 17, 0.31, 0.27, 4 is 0.11, 5 I do not know, and 6 is 0.01. Okay, so the first question I'm asked is to figure out what the 5 is. So all of these numbers should add up to 1. So what I can do is I can use the sum feature of Excel, and I can just add up the numbers I was given, and then subtract that from 1. So 1 minus that, and I get 0.06. Okay, so that means means the likelihood of having 5 children in this town is 0.06. What is the probability that a randomly selected family will have at least 2 children? Okay, so let's go back to my chart here. At least 2. So that means I could have 2, I could have 3, I could have 4, I could have any of these right there, right? So that's what I want to add up, are those probabilities that correspond to just those categories. And so there's a 76% chance that that's at least 2. Okay, then we get this inclusive and exclusive. So inclusive, if I'm going 1 to 4, then I want to add up those numbers. The 1 all the way down to 4. If I'm doing exclusive, that means I'm skipping the border numbers. So I'm not doing 1 and 4, I'm just doing 2 and 3. So I just want to add up 2 and 3. And those would be the 2% for that. So 86 and 58. All right, the next question, what's the probability that a randomly selected family will have at least 1 child? So if I go back, at least 1. So in this case, we're thinking at least 1 means all of this, which means it doesn't involve the 0.07. So I can just use the at least formula, 1 minus 0.07 to get 0.93. And then good. The other way to do that is I could have added up all of those numbers to also get 0.93, but obviously 1 minus 0.07 is a little bit easier. All right, and last but not least is what is the mean and standard deviation for this distribution? So I would suggest having the formula chart handy on that. I did give some Excel hints as far as how to do this, so I'll kind of remind us how to set that up right now. So if I want, for example, the mean, I'm going to, sorry, let me slide this down so I have a little bit of space to work. Okay, so if I want to calculate the mean, then I want to create the x times the probability of that observation column. So I'm literally going to click on the first box times the second box, hit enter, and then I'm going to drag that down to the bottom, and then I just want to sum that up. Okay, so my mean is 2.4. Standard deviation, I need an x squared times the probability of that observation happening. So I need that column. So I'm going to click on the first box, squared times the probability. Hit enter, drag that down. Okay, now a few more things to do here. I still need the sum. So I'm going to add up all of that. Then I also need the mean squared. And then what I'm going to do, according to the formula that I have on the sheet, is I'm going to subtract these two numbers and then take the square root. So that number right there is the variance, and then the square root of that number, the 1.7, happens to be my standard deviation. So the standard deviation is 1.3. All right, yay. Number 11, we're asked to look at two situations and identify whether or not they're binomial, and if not, then sort of explain what the violation is. So in the first choice, we have 10 dice that we roll, and we're going to count the number of 6 as I roll them, in which case I've got a fixed number of trials. Each toss is independent of the other. There's clearly a defined success and failure. Either it's a 6 or it's not. So this one is a binomial. And let me kind of write that down again. So fixed trials, the check. They're independent of each other, check. There's clearly a success and failure. Okay, so it satisfies all the binomial distribution criteria. The second one, it's estimated 43% of people sleep regularly with a nightlight in the room. X is the number of people who sleep regularly with a nightlight. Okay, we clearly have a success failure, so either you sleep with it or you don't. Whether one person has it is in their room is independent of another. But the problem is we don't have fixed trials. So it's not binomial, and the reason is no fixed trials. All right, number 12. Studies indicate that 70% of the families of Bluebell, both the husband and the wife, work. If 7 families are randomly selected from Bluebell, what is the probability that? Okay, so let's kind of checklist a few things. We just talked about binomial. So is this particular variable a binomial variable? We've got a fixed number of trials. We know there's 7 people. We definitely have a success failure. So either they work or they don't. And each husband and wife are independent of another. So one family doesn't really have any control of another family. So this clearly is a binomial distribution, which means I can use all of our binomial distribution formulas. So exactly 6 of them work. That would be a binomial PDF. And let's see, so let's go into Excel here. And let me kind of get another screen that I can work on. Okay, so binomial PDF, so binom, and right there binomial distribution pops up. We're looking at the 6th of the 7. So we're looking at trial number 6 with a total of 7. Probability is 0.7. And for a PDF, I want to type in the words false. A CDF would be true, PDF is false. So I get about 24%, 0.24. So 6, 7.7, and false is how we got it in Excel. And different calculators are going to have a little bit more than, we're going to have different commands that they would use on that. More than for work. Okay. So let's kind of think a little bit of theory here. We're not going to work out all the numbers, but if I just think about, I've got 7 families, right? More than 4 means I'm looking at the numbers for 4, 5, 6, and 7. So I'm looking at those, right? So there's kind of 2 routes I could go. I could calculate 4 different PDFs. So I could calculate the PDF of 4, the PDF of 5, etc., etc. The other way I could do it is I could look at a CDF, and I could just figure out the CDF, so all the way up to 3, and then subtract that from 1. And that sounds like it's a lot easier than doing it 4 times, so that's what I'm going to do. I'm going to do a binomial CDF. I'm going to go up to 3, so this will give me 3 or less. Trials, there are 7. Probability is 0.7. And this time I want true to get the CDF function out of Excel. And so all the way up to 3, it adds up to about 12.6%. So then to get 4 or more, I just want to subtract that from 1. All right, so about 0.874 on that. So that was 1 minus a binomial CDF of 37.7 in true, and that worked out to be 0.874. All right, mean of the distribution. Okay, so now we want to go to our formula chart. The mean of a binomial distribution is n times p. So in this case, n is the total number of trials, or 7, and p is the probability of success. So the mean is 4.9. And then standard deviation for a binomial is the square root of npq. So in this case, n times 0.7, q is the failure. So if 0.7 is the success, then 0.3 has to be the failures. And if I type that into a calculator, I get 1.21. All right, last but not least, so I'm just going to warn you about this question. So one of the questions on the test, I'm going to throw something non-traditional at you and see what kind of statistics principles you come up with. So it's going to be stuff that we've covered. It's not going to be exactly this question, so don't think I'm going to switch the percent to 6 and go, oh, see what you can do. But I'm looking at there's some sort of mastery or understanding about what these statistics principles tell us. So I'm going to deem this one an investigation question, where there's some sort of pattern I want you to look at, and I want you to tell me what statistics principle the pattern is illustrating. Okay, so let's read this question and kind of talk through it. An airline, believing that 5% of the passengers failed to show up for flights, overbooks, sells more than there are seats. Suppose the plane will hold 265 and the airline sells 275 seats. What's the probability that the airline will not have enough seats so someone gets bumped? Now, for those of us that have flown places, this is true, that they actually will sell more seats, and sometimes they get caught by having more people show up than they have chairs, and some people have to wait for another flight. So this is actually real life statistics that happens all the time. All right, so let's think about what this sounds like. We have, let's see, there's 275 seats that were sold, and we want to know what's the likelihood that 265 or more show up. In other words, what percent of the time is someone going to be mad that they have to get bumped from their flight? Well, the fact that there's 275 seats, that sounds like a fixed number of trials to me. And let's see, it's one passenger independent of another. Then reasonably I can say, so I understand if there's a family that's late, then the dad being late causes the mom to be late, but we'll pretend that they're just all independent people. And the 5% means either they show up or they don't, right? So what I want to know is I want to look at what percent of the time would I expect more than 265 people to show up, given that there's 275 seats, right? So, here's 265 seats, 266 seats, 267, all the way down to 275. I want to know this part. What's the percent of the time that I would expect to see something like that? So this sounds a lot like a binomial CDF. Now a CDF will give me less than, so I can use a CDF to figure out all the way from 0 to 265, and then subtract that from 1 to get this above 265 mark. So that's what I'm going to do. I'm going to do 1 minus the binomial CDF of 265 of 275. Now, this is where, when I say investigation, you got to be a little clever about this. They told me 5% don't show up, but what I'm looking at, I'm thinking about what percent of the time do people show up. So even though the number says 5%, that's not what I'm defining as my success. My success is who shows up, right? So the percent of the time that that happens would be 0.95. And since this is a CDF, then I want to use the true. And so let me go type that in a calculator. I can't get it on there. Okay. So equals binomial distribution number 265, 275. I'm saying 95% of the time they will show up, and I want true. Okay, so 88% of the time I'll have up to a full plane, up to 265, which means if I subtract that number from 1, then 11% of the time I would get something above 265. So 0.116. So 11.6% of the time I would get someone, I would have more people than are there to fill the plane. So in real life, you got to think, if 11% of the time, so that's like close to 10, right? So every 10 flights, one flight they get caught, more people show up, they're still making money on the other 9 flights. And are they making enough money? I mean, think about people who get bumped. They get comped tickets, they get hotels, right? But you've seen how much airline tickets cost. So they're making more money off of this. So it's actually in their best interest, sadly to say, to overbook flights so that the 1 or 2 times out of 100 they get caught, they still have more money and they can afford to, oh, you want free dinner? Here's free dinner. There you go. Sorry to make you wait in the airport another couple hours.